Hello, everyone. My name is Simthembile Dlamini, and I'm grateful to have this opportunity to talk about the project. In fact, one of the projects that I've done in my PhD studies. So I'm supervised by Professor Roy Martins and Dr. Shian Jellicoe. As you can see the title, Exploring Redshift-space distortions by combining the future spectroscopic surveys. So, at first I thought maybe I'll be able to just talk more about a couple of projects which I've done. But when I saw the time, then I thought, okay, no, it's fine. Let me just stick to at least one. And because this one is already published, so I think I chose it as a good one to just talk about, which is part under the exploring the redshift-space distortion. So this one is basically like we're constraining the primordial non-Gaussianity. I will keep referring as FNO, which is basically like the measure of the parameter that measures a large-scale structure. So the surveys that I'm talking about, we're using these instruments. So the SKAO and the dark energy spectroscopic instrument, which is the DESI in short. So, and the idea why we're using these future spectroscopic surveys is that they help us to kind of map the larger areas in the sky, which is more relevant for the work that I'm just presenting now, because as I said, the non-primordial Gaussianity, it actually appears in a very large scale. So we've been meaning that we need like bigger volumes and larger sky areas, and these machines, they help us to kind of observe those areas. I don't think I will have to say more on intensity mapping because Yinzi just explained it well. But maybe again, just to emphasize the point that I just mentioned, it is easier to work on intensity mapping as compared to the traditional way of doing the observations, where you have to kind of like do the count of individual galaxies. And as I said, very large areas of the sky will be mapped by these machines. Okay, so it's all good, all nice, until we have problems. Because with the intensity mapping, we have a problem of foregrounds. So, as I said here, we basically how to model noise as well as the systematic. In this case, what I refer as a systematic is the foreground problem. As we know that the signal is actually buried in the foreground. So how do we do that? We model using the K-cut, which is, we basically say, okay, we have to avoid this, using this K, 0.01 HP megaparsec, so that at least we do the foreground avoidance. And then the noise issue, which basically comes from an example. An example here, as I said, we're using two surveys to do to constrain our FNL. So what then we do is we do the so-called cross correlation, which is basically the multitracer. And since we're doing the multitracer, we got the information from the galaxy survey. In this case, I have DESI as for the galaxy survey, the PGS and the ELG. And for the intensity mapping, I have SKAO, band 1 and band 2. So it's both low redshift and also the high redshift surveys. And we do the cross correlation in between. So what I was saying is, then the short noise, which comes from the density number count,